So the next piece of the puzzle on the server side is the LockManager service. And this is really the workhorse for this particular class. So we're going to spend some time on this one because it's quite interesting. The first thing to note here are the two auto-wired fields. The first auto-wired field is the one that's going to be connected to an AsyncTaskExecutor. And the second auto-wired field is the one that's going to be connected to a concurrent hash map. And as we saw previously, the auto-wiring here is satisfied by this bean, which is the factor method that makes a new executor that will create a new virtual thread per task. And the second one we have here is this one, which is the concurrent hash map, which again comes out of the server bean right down here. And this is going to do some interesting things. So let's kind of talk through this real quick. So the first thing to note here is we have an array blocking queue that's parameterized by lock. So an array blocking queue is this Java class that is a synchronized collection, and it implements a bounded buffer. And the idea here is if the buffer is full, you can't add things to it without blocking. If the buffer is empty, you can't take things out of it without blocking. But if it's not empty or not full, you can add and remove things without blocking. And the way we're going to use it is if people follow the protocol, then we're going to have a fixed number of locks, because that's what it's parameterized with, in the array blocking queue. And the acquire and release methods are going to either try to remove one or more locks or permits from the array blocking queue atomically, or they will try to add one or more locks to the array blocking queue also atomically. We'll see that acquiring is much more complicated than releasing. And then we use a map that just maps the lock manager to its array blocking queue, and that's what's auto-wired together using a concurrent hash map so that these updates and reads and so on can occur very efficiently in a multi-threaded program that's mapped to multiple cores so things truly can run in parallel. The other thing I'll note here real quickly is that concurrent hash map is very highly optimized for concurrent and parallel access and updates, such that as long as things hash to different parts of the hash table, then everything can run completely in parallel without having to worry about contention for any given shared lock. In fact, only write operations have any contention whatsoever, and that's done in a very clever way using low-level compare and swap operations to do essentially a lock-free data structure. So that's what this thing is, and you're going to see how this plays out here shortly. So let's go take a look at the create method. Create is pretty fun. It takes a permit count that came from the client, and it's going to return a lock manager. This code will run in the context of the HTTP worker thread, because we're not going to do anything fancy here. This shouldn't take very long to initialize. We make ourselves a new array blocking queue with the number of permits that the client requested, and the value here set to true. And what that means, of course, is that the threads that need to wait on permits will end up queuing in, first out order, or FIFO order. And that allows things to be fair and avoid starvation. Once we have got ourselves an initialized array blocking queue with this capacity, which is a fixed capacity, we then add a bunch of locks to it. And here's how we make the locks. So we take the permits count, and we use the streams mechanism. This is just a sequential stream, nothing complicated required here, to make ourselves permits number of integers from 0 to permits -1. We turn those into strings, and then we go ahead and make a new lock object for each of those strings. So again, if you come over here and you look at lock, you can see it has a constructor that takes a string, and it makes a lock, and that lock is then used here in order to have a list of locks. So we got a list of locks there, and we then go ahead and generate a unique ID for the lock manager. This just uses a helper class that's called UUID, which stands for Universally Unique ID, and we make ourselves a random value and turn it into a string. So that's going to make that. So we have a lock manager then with this number of permits and this unique ID. And then we store that lock manager in the lock manager map along with the available locks. So that's going to be the part of the state that's been updated here by create, which is, again, why it's a post method. That'll be a great quiz question, by the way. Why do we use posts? Because we are updating the server state. Then we return the lock manager. So that's how things work. So now what happens there is that LockManager will be sent back from the service to the controller, from the controller back to the client proxy, which will then turn it into something that, as we'll see here shortly, can be used by the client in order to acquire or release on a given manager. Now let's go take a look at something much more interesting. This is the first of two acquire methods. And this acquire method, as you can see, is marked with the async annotation. And what that means is that when it's called, remember it's called down here by the controller. Let's see where it calls it. When this method is called by the controller running in the HTTP worker thread, that is going to cause the executor that we have here, this guy, which is what we wired, that's going to be used in order to go ahead and invoke this method in its own thread of control. So it's going to be run in its own thread, and we didn't have to spawn that thread. That thread was spawned for us automatically by Spring because we put the async annotation on the acquire method. And again, recall we get the LockManager and the callback here. Now we're going to do a couple things. Some of them are pretty obvious. The first thing we're going to do is we're going to go look up the LockManager in the LockManager map in order to get the array blocking queue that contains the available locks. And that's why we had to have that equals method defined on LockManager so it can go and search using hashing and the hash code method. So it can go and hash and find the right instance and return its array blocking queue. If something weird has gone on, like somebody mucked around with a LockManager and changed its name somehow, in that particular case, then we won't find anything. And so we're going to create a new illegal argument exception and make that be what is returned back to the client using our onError hook method on the callback. Let's assume, for sake of argument, though, that nothing has gone awry. So now we're going to make a method call to tryAcquire. And tryAcquire takes the callback and the array blocking queue, and it will try to acquire a lock without blocking first, but it will block if it absolutely has to. So let's go take a look at that method. Oh, and you can also see if this fails, if an exception occurs, we're going to throw that exception, or we're going to make that exception return back to the client using the callback. So here is tryAcquire. So you'll notice I put a lot of logging statements in here, so it's easy to tell what's going on when we run the program. So first thing we do, we try to acquire a lock without blocking. And we do that by calling the poll method on the array blocking queue parameter. The way poll works is if we acquire the lock right away, then the lock comes back to be non-null. We just log the fact that it worked with a non-blocking mode, and then we fall down through this if-else statement, and we notify the callback we succeeded by giving it the lock we just obtained in a non-blocking way. However, if we don't actually acquire the lock through polling in a non-blocking way, then and only then are we going to say, Uncle, can't make any progress. Let's go ahead and block until we get this lock. Now, we have a couple choices there. In this case, we're just going to block. Take is a blocking operation that will put this thread, it'll suspend this thread until there's an item for it to get. So it blocks it. We could have sat there in a loop and polled repeatedly. But for various reasons, I didn't want to do that for this example. So this is the one case where things will actually block. So this is what we might call a lock-free optimization phase up here with poll. And if we succeed, we're done. And if not, we wait. Very canonical way. If you take a look at the Java concurrency package, you'll see this type of idiom used all over the place. At any rate, we either block or not block, and we get a lock, and we call the callback on success, and that triggers the call to go back to the client with the lock that we got. All right, now let's take a look at the fun implementation. This is the one that's much more complicated. This is the acquire method that takes a permits count. And you can see here, this is going to return a deferred result, which has a list of locks. Oh, I should also mention, when this method returns, when the tryAcquire method returns, and when the acquire method returns, the virtual thread that was created asynchronously goes away. Long before that, the HTTP worker thread that called acquire has gone and been recycled back into the pool of worker threads getting incoming requests. That's all done behind the scenes. You don't have to worry about that. This version of acquire is slightly different, and we do this intentionally just to show two different ways of doing things. This one's going to return a deferred result which contains a list of locks, because now we're getting back multiple locks that we've requested. So to do this, we first create a deferred result for a list of locks, and we're going to check to see then if we can find the array blocking queue corresponding to the lock manager. If we don't, if we get back a null, we've got a problem. The person passed in an invalid lock manager, so we are going to send back the illegal argument exception as the error result going back to the client. If all goes well, however, then we get to the part that's really interesting. So if we get to this far, that means we found the available locks, we found our array blocking queue, and now we will manually run the computation off of the servlet thread, off of the HTTP worker thread. So we're going to say mExecutor, which is that one that's bound to the thread pool, make a virtual thread per task executor, that executor. We're going to submit this runnable. We'll talk about this runnable in a second, where that comes from. And that will then go run in the background. And then what's going to happen here is if for some reason we can't submit, which would be very weird, we're going to set the deferred result right away and bail out. Otherwise, everything worked okay, and we're going to return the deferred result. So in any case, this operation that is going to be submitted, the runnable we're about to look at, is going to run in a virtual thread in the background, but this method will return right away. And then, of course, the corresponding method here on the controller will return right away, and that particular HTTP worker thread or servlet thread will no longer be involved at all in what's about to happen. So what we're going to do is focus here where we submit a runnable. And notice we pass in the number of permits, the array blocking queue, and the deferred result to this factory method called getRunnable. And this is where the core logic for doing essentially a lock-free implementation of a semaphore for doing multiple permit acquisition using an array blocking queue lurks. And this is quite an interesting algorithm. So it takes the permits, the available locks, and the deferred result, which returns a list of locks. So what we're going to do is we're going to return a runnable. What is a runnable? A runnable is a functional interface defined in Java. It's been around since the very beginning. It has one method called run that takes no parameters and returns no result. So we're going to use this to run something in the background in a virtual thread. And so what we're doing here is we're returning a runnable, and we're using a lambda expression to create the runnable that we return, which is more streamlined than doing something like an anonymous inner class. So the runnable that comes back that's going to run in the virtual thread is first going to make a new array list of locks of the capacity of the number of permits. So these are the acquired locks. These are the locks we're trying to build up to return back to the server. Sorry, return from the server back to the client. And the idea here is we're then going to go into a loop, and we're going to keep looping until we have acquired the number of locks that we need. So permits is what we're looking for. And while try_acquire doesn't return permits after it's called, we continue to loop. And this could loop for a while. This is the pros and cons of a lock-free algorithm. So we're not actually going to block at all here. We're just going to spin. And when you see the code, you'll see sometimes you spin for a while, sometimes you don't. But that's one of the characteristics of a lock-free algorithm. So we pass in the available locks, the ones that are for use, and the acquired locks. So the available locks is the array blocking queue. The acquired locks is just a list of locks we're trying to build up to match this number of permits. So let's go take a look at try_acquire, because this is quite interesting. So here's try_acquire. It takes the array blocking queue of locks that are available and the list of locks we're trying to acquire. So the first thing we do is we perform a non-blocking poll. And if we get a lock, in other words, if we get a lock from the non-blocking poll, we're going to go ahead and add that lock to the list of acquired locks. And then we're going to bail out after returning the number of locks we've gotten so far. In other words, the size of acquired locks. And if it turns out that that size equals the permits, so we've got them all, we wanted 5 permits. We got 5 permits at this point. Then we break out of the loop. We set the result of the deferred result to be the list of locks we just acquired, and we're done. However, if we don't acquire a lock through polling, now we've got to do something kind of funky. Because we're not locking things, we're only spinning, we're only doing a lock-free algorithm, we have to give up all the locks we've acquired. Let's say we wanted 5 and we've got 1. We'll give up that 1 lock. Let's say we wanted 5 and we've got 4. Oh, well, we're going to give all those locks up. And the way we do that is we put them all back into the available locks array blocking queue in a non-blocking way. All those locks are basically put back in. And the reason for doing that is we want to avoid deadlock, and we want to avoid making sure that we eventually succeed. And so by doing this, we then give other threads a chance to make their play to get everything. We then clear out the list of acquired locks and return 0, indicating, hey, we didn't make any progress at all this time, and so start over again. So remember, the reason why we're doing this is there could be multiple threads simultaneously trying to acquire multiple permits. Let's say, for sake of argument, that there are 2 permits that are available, and there are 2 threads, each of which wants 2 permits. A mistake to do here, which we don't want to do, is have each thread grab a permit and then block, waiting for the other permit, which of course it will never get because the other thread holds it. So that would be a classic example of deadlock. So what we do is we try our best to try to do it in a non-blocking way. If we get everything we need, we're done. If we don't, we throw it back in the pool, and someone else can contend for it. Now, as you might expect, this particular algorithm is going to work very well and be efficient if there's not a lot of contention. If there's lots and lots of threads contending for the locks, there's going to be a lot of contention, and it doesn't work so well. But that's one of the pros and cons of using lock-free approaches. So that's basically how the second version of acquire works. Release has 2 versions as well. Mercifully, they're much easier. When release is called, where we release 1 lock, we get the lock manager, and we stick this. We basically go ahead, and if we get the array blocking queue, we simply put the lock back into this queue in a non-blocking way, and then we return whether or not that succeeded. It should succeed as long as the client, the caller, doesn't violate the protocol. What does it mean to violate the protocol? You can violate the protocol if you, say, have a lock manager with 1 permit, and then you call release multiple times, more than once, in which case you'll be putting back something that shouldn't be there. So then this will fail. But we can at least figure out and tell the caller that that's happened if they try it. And it won't have any effect here. It won't cause any harm. So you can see we returned false if something went wrong. Likewise, for releasing the list of locks, same basic idea. We get the available locks from the LockManager map. And assuming we succeed, we're going to release all the locks. And to do this, we use a clever stream approach where we're going to convert the list of locks into a stream of locks. Then we're going to, for each of the elements in the stream, we're going to put it back into the underlying array blocking queue using offer, which won't block. And if everything returns true, this returns true. But if anything doesn't return true, all match returns false, which is, again, an indication back to the client that something's gone wrong. OK, so that is basically the service implementation. As you can see, there's a lot of stuff going on here. But the nice part about this is, from the client's point of view, all of this low-level gobbledygook and the sophistication of this algorithm is hidden, and it just has to worry about creating a lock manager with a certain permit count, acquiring either 1 or multiple locks, and then releasing those locks at some point when it doesn't need them anymore. So we'll talk about the client side here in just a moment.